Hello, in this second equilibrium video, I'm going to, for the benefit of my students, just give a couple of examples of questions that you'll be expected to know in a general chemistry class that require ice tables to solve. There are lots of other questions in equilibrium that you'll have that don't necessitate ice tables, but ice tables tend to be the ones that cause the most grief to students. So I will focus on those that I know are going to be problematic. Okay, so this first question, we are given a balanced equation. So I'm going to record the equation here. So nitrogen gas plus oxygen gas. We're told this is at equilibrium with 2 lots of nitrogen monoxide gas. And we're given some conditions. We're told that initially we have a concentration of nitrogen that's 0. So we don't have any nitrogen to begin with. Neither do we have any oxygen. But we're told we have 0.01 molar quantity of nitrogen monoxide. And then we're asked at equilibrium, what's the concentration of everything? So initially, if I just give you some nitrogen monoxide and I walk away, come back, once this thing reaches equilibrium, what will be the concentration of everything? Okay, so I need to look at the change, and then finally the equilibrium, which is what I want. So we have to look at shifts. Well, you can only shift away from something. You can't shift away from nothing. So I have to decide where I'm going to shift. You always shift towards a 0. So I know that these pluses can only increase, they can't decrease. Whereas this positive number can only, well, it can decrease and increase. But if I increase on the left, I have to decrease on the right. Then I increase or decrease respectively by an unknown amount x. So I increase by an unknown amount x. For nitrogen, I increase by an unknown amount x for oxygen. Now it's a 1-to-1 ratio because they're a 1-to-1 ratio in the balanced equation. I decrease by twice as much because there's a 1-to-2 ratio with reactants and products. So I decrease by 2x, where again, this 2 is because of that coefficient 2. The equilibrium concentration is the sum of the initial and the change. So I have 0 plus x is just x. 0 plus x is also x. And then 0.01 minus 2x is 0.01 minus 2x. So you essentially add these two to give that one. Okay. We're also given the equilibrium constant for this expression. So we're actually given Kc, which is 0.055. So that's what we were told. So let's scroll this thing down. Okay, so we've started set up our ice table. So we can say, let's write a Kc expression. So Kc is NO squared divided by N2 O2. That's our law of mass action expression. Well, this is equal to 0.055, no units. And this is equal to the concentration of N2 at equilibrium. The products of NO at equilibrium. So it's this thing squared. So it's going to be 0.0100 minus 2x squared, okay, divided by the concentration of N2 multiplied by O2, both of which are x, so it's just x squared. Okay. We would then have to FOIL the numerator, so we could take this numerator and we could FOIL it. So if it's been a while since you've FOILed something, you would have to FOIL that away. So this video is not a reminder on how to FOIL, but let's assume that you FOILed it away. So we know that 0.055, if we FOIL that and we essentially bring everything to one line, we have 4x squared minus 0.0400x plus 0.0001. And then if we set everything equal to 0 by transposing everything onto one side, we have 3.945 x squared minus 0.0400 x plus 0.0001 equals 0. So this is the form of the equation that we want, so that we can use the quadratic. So we've got the equation in an ax squared plus bx plus c equals 0 form. And that's essentially always the form we want our equation in to solve the quadratic equation. Okay, so let's scroll this down. I don't know if I'll need the whole page, but let's at least try and get this done on one page. So remember our quadratic equation. We have x is equal to minus b plus or minus b squared minus 4ac, and the whole thing is over 2a. Okay, so we actually plug our data into this now. We would have x is equal to minus b. Well, b is already minus, so it's negative 0.0400 plus or minus negative 0.0400 squared minus 4ac. A is 3.945. C is 0.0001. We've got to remember to square root this whole thing. And then we divide the whole of that expression by 2a, which is twice 3.945. So it's definitely important that you take your time when you do this. A lot of little squiggly things can go wrong. So we do that, and then we always get two numbers, two solutions. Only one of them can make physical sense. So we get x is equal to 5.664 by 10 to the negative 3, and we can return the unit now. Remember, we're solving for molarity. Or the other solution is that x is 4.475 by 10 to the negative 3. Now, they both can't be right, so this is the correct answer, and this one is incorrect. So only one of them is going to be possible. And how you would tell, if you have two positive values, plug them back in, and only one of them will preserve reasonable answers. So if we look at the incorrect option, if we were to plug this back into our ICE table, it would render a negative value. So it's incorrect because it would give a negative molarity. in the ice table, which is impossible. Okay, so there's only ever going to be one answer, although there's two solutions to the quadratic. So finally, to answer the question, so remember we had our ice table here. So I know what x is, so now I can plug x in. So I already know what N2 and O2 are, they're just x. And I can subtract two lots of x from 0.01 to figure out what the equilibrium concentration of NO is. So I can finally say that N2 equals O2, which equals x, which just equals 4.475 by 10 to the negative 3 molarity. And I know that NO is 0.01 minus 2x, which is two lots of this, which is 1.05. I'm paying no attention to sig figs here, just the ballpark answer. Okay, so that's a first example of an ice table, and we will have a second look at an ice table right now. Okay, so I'm going to, so let's look at a second example of an ice table question. Here we're going to have a look at something in pressure units. So here's a second example. So let's take carbon monoxide gas and water vapor in equilibrium with CO2 gas and hydrogen gas. And here we're given some information about the pressure. So we're given the initial pressure in units of atmospheres. And we're told that we have 1.7684 atmospheric pressure. We're told that we have 2.3237 atmospheric pressure here. And we don't have any of this. Again, I'm not interested in this question in sig figs. This is just the only teaching moment in this video is just the process of familiarity with ice tables. We need the change in pressure in atmospheres so we can get the equilibrium pressure in atmospheres. Okay, we are told that Kp is equal to 0.0611. Now, we can immediately see that if we wanted to, we won't, but if we wanted to, we could get Kc because we've got equal number of moles on reactant and product side, so delta N is 0. So Kp is equal to Kc. Okay. We can't shift away from 0, we have to shift towards it, so we know that we're going to shift away, we're going to shift right, away from the left towards the right, towards the 0. So we have, everything's a 1-to-1 ratio, so this would be minus x, this would be minus x, this would be plus x, and plus x. Again, these x's are just very constant, not constants. These x's are amounts, and the ratio is the molar coefficient ratio. Equilibrium is just the sum of the initial and the change. So we have 1.7684 minus x, 2.3237 minus x, and then we have no plus x is just x, no plus x is x. Okay, So our Kp, we just have the partial pressure of CO2 multiplied by the partial pressure of H2 divided by the partial pressure of CO multiplied by the partial pressure of H2O. That's equal to 0.0611, which is equal to x squared divided by 1.7684 minus x multiplied by 2.3237 minus x. Okay. We know from the initial question that we want to get this in square form, so we can use the quadratic. So let's go ahead and do that. So we've got 0.9389 x squared plus 0.2500x minus 0.25107. Again, no adherence to sig figs here. I'm not really paying attention. But this is our ax squared plus bx plus c is 0 form of the equation. So we can use the quadratic. Remember our quadratic, we've got x is minus b plus or minus b squared minus 4ac. That whole thing is square rooted. And then the whole thing is over 2a. So this is equal to minus 0.2500 plus or minus 0.2500 squared minus 4.9389 minus 0.25107. And that whole thing is square rooted. And then the entire expression is over 2a, which is 2 lots of 0.9389. We get two solutions. Only one of them makes any physical sense. So let's see what the two solutions are. We get x equals 0.4008 atmosphere. Remember, it was in units of atmosphere. Or x equals minus 0.6671 atmosphere. Well, this is not possible. There's no such physical thing as a minus pressure. Minus pressure here is not a negative pressure. Negative pressure refers to a change in pressure. An absolute negative pressure has no physical meaning. So this is the correct value. Okay, so we know, if we look back at our ice table, we already know the equilibrium pressure of CO2 and H2, and we can just plug in X with these variables to get the equilibrium pressure of CO and H2O. And just to do that for my students, to do that, actually, I haven't finished that in my notes, which is kind of funny. But I will just say that the pressure of CO2 is equal to the pressure of H2, which is 0.4008 atm. And then the pressure of CO get rid of that little scribble. The partial pressure of CO at equilibrium is equal to 1.7 684 minus 0.4008, and obviously that's atmospheres, and the partial pressure of H2O is equal to 2.3237 minus 0.4008 atmospheres, and that would equal, etc. Okay, let's see if I feel like doing one more example. I have another example I can give you quickly. Let me see, I've got my notes just off camera here. Yeah, let's finish with one example. No, actually, I already gave that example. Maybe we'll just leave it there and keep it short and sweet. Yeah, I think we'll leave it there, keep it short and sweet. So again, you know, obviously you'll be given homework questions, but this is the big type of question, ice tables. In other topics in this course where we look at acid-base equilibria, we'll look at different ways of doing ice tables beyond using the quadratic, but we'll leave that until we look at acid-base equilibria.